All right, guys, the final topics for chapter 5 are power and then force versus displacement graphs. So let's start with power. There are two ways to look at power, and you guys all have an idea of what power is. You know, it's a term we use in everyday life, but in the physics sense, there are two ways you could look at power, and these are equations. The first way to look at power is you could say that power equals the work done per time. Okay, the work done per time. Or you could also say that power is equal to energy used per time. Which way you look at it depends on the situation. You know, if you're talking about a car, you know, like the power output of this car's engine. You know, could we talk about the work done by the engine of the car? Yeah, the engine of the car is doing work as it moves the car. Okay, so it would probably make more sense if you're dealing with a car to look at it this way: work per time. Now, if you're dealing with a light bulb, if you're talking about the power of a light bulb, is the light bulb doing work or is it using energy? It's using energy. So which way you look at it depends upon the situation. But either way, look, what's the unit we use for work? Joule. Time is measured in second. What's the unit we use for energy? Joule. What's for time? Second. So either way, you get joule per second, and a joule per second, every single person in this room has heard of the name. There's a name for this. A joule per second is referred to as a watt. Okay? A joule per second is a watt. So for example, like you go to Home Depot, you buy a light bulb. Let's say that this light bulb here is 50 watts. What is that telling you? If you buy a 50-watt light bulb, you screw that light bulb in, turn it on, and what's going to be happening? That light bulb is going to use what? 50 joules of energy every second. So what if that light bulb is on for 10 seconds? How much energy would it use? 500 joules. All right, thanks. And by the way, what I was doing there, I'm just using this power equation right here. So if you want to know the energy used, if you rearrange the equation, it's power multiplied by time. So 50 watts, 50 joule per second for 10 seconds. The seconds cancel and you get 500 joules. Now, I want to mention here a unit for energy, because like if you any given month in your house, like just using this as an example, a light bulb that's on for 10 seconds, that uses 500 joules. So when you get your electric bill from Edison, when Southern California Edison sends you the electric bill, are they going to tell you how many joules of energy that you used? No, because that'd be ridiculous, right? You're using like millions and millions and millions of joules every month in your house, right? By just turning your hair dryer, your lights, your TV, your computer, all the electrical devices. So what Edison uses is this unit called the kilowatt hour, which I want to just briefly mention. You're going to see this second semester. So kWh, if you look at your electric bill, you're going to see kWh, which stands for what? Kilowatt hour. All right, so let's start. What is kilowatt? Let's figure out what a kilowatt hour is. A kilowatt is 1,000 watts, which is 1,000 joules per second. And then what's the hour? How many seconds are in an hour? 3,600 seconds, right? Because we want the units to match. So what happens to the seconds here? The seconds cancel, and we get 3,600,000 joules. That many joules is equivalent to 1 kilowatt hour. Guess how much that costs? And I'll be honest, I don't really know. I haven't looked it up, but I have a ballpark idea. Just ballpark, nickel, dime, quarter, dollar, $10, $100, within how much would that be? Nickel, dime, quarter, dollar, $10, $100 for 1 kilowatt hour for 3,600,000 joules. It's a dime. It's about a dime, 10 cents. So how many of you have electric bills that are like $200 a month? My electric bill is like $80 a month, but I know a lot of people. I mean, we're always turning light. I'm like turn the lights off. Lights off. We have all the low energy stuff. But yeah, if your electric bill is like $200 a month, so that's going to be what, 2,000 kilowatt hours at 10 cents per kilowatt hour. Is that right? So anyway, the kilowatt hour. Oh, and then the other thing I want to mention. Hey, in everyday life, what's a common unit that you've all heard for power? Has the word horse in it. Horsepower. You've all heard of horsepower, right? So horsepower and watts do the same job, right? If they talk about, the power output of a car is frequently measured in horsepower. 1 horsepower is equal to 746 watts. So horsepower and watt does the same thing. All right, so let's look at an example of this. All right, so we got this guy. It's kind of hard to see on the screen, but this guy is pushing on a refrigerator. Can you guys see the fridge? There's a refrigerator right there. So this guy pushes on a 500 kilogram refrigerator across a level floor with a constant velocity. The force he exerts is 900 newtons. So he's exerting a 900 Newton force for a time of 5 seconds, and he pushes the refrigerator. So move the floor. Here we go. So he pushes the refrigerator a distance of 10 meters. So using this info, it's a very quick calculation. I want you to calculate the power output of the dude. What's the power of the dude? So take like 2 minutes. It's pretty quick. Finding the power of the dude, the power of the guy. So hey, are we going to look at this as work per time or energy per time? Work. I'd look at it as work because the guy's doing work here. So power of the dude is going to be the work of the dude divided by time. Okay, we can easily find the work of the dude, right? Do we know the force of the guy? Yeah, 900 Newton force for 10 meters. Are those parallel to each other? Yeah. So what's the power of this dude going to be? Well, he does 9,000 joules of work, right? 900 times 10. 9,000 joules in a time of 5 seconds. What's a joule per second called? A watt. So this is 1,800 watts, which I believe, I just made this problem up. I think that's pretty unrealistic. Do you guys remember the video on Friday? The professional cyclist that set the record for fastest bike? What was the fastest speed? 83 miles an hour. And to get to that speed, his power output was, anybody remember? I watched the video 6 times on Friday, so I know every part. 800 watts. That cyclist, his maximum power output was 800 watts. So could this guy here crank out 1,800 watts? Maybe, because he's only doing it for how long? 5 seconds. Could he maintain that for like 5 minutes? No. But I think, is that, I'm not totally positive if that's realistic or not, but it could be. I don't know. 1,800 watts. Hey man, how many horsepower would that be? How would you convert this to horsepower? 746 watts is 1 horsepower. So you can figure out like how many horses. He's got like 2 point something horsepower, which hey, look, what's the difference between that guy and a horse? A horse could do it all day long, whereas like a human being could maybe crank it out for like 5 seconds. Okay, and you know what? Hey, real quickly, just to to tie up chapter 5 here, look, I want to just talk a little bit about this situation. This is a good situation to understand, and I don't want to make this too lengthy or not. But look, this guy is pushing this with a constant velocity. This refrigerator is moving at a constant velocity. What does constant velocity tell us? Acceleration is 0. So what's the net force? 0, because F net equals ma, right? F net equals ma, right? So if your A is 0, then your F net is 0. Well, how is the net force 0? Well, the dude is pushing to the right. This is the force of the dude, 900 newtons. What has to be present here? Friction. There has to be a frictional force equal to what? 900 newtons, right? Because the net force has to be 0. And then, of course, we have mg down and normal force up, but those don't factor in here. Now look, chapter 5, what is work net equal to?
0.
Work net is always change of kinetic. It's a pretty awesome equation. You know, would I have ever thought of that on my own? No. But then somebody pointed it out to me and I was like, cool. Net work is always equal to the change of kinetic energy. Okay, so look, if this thing moves with a constant velocity, what's the change of kinetic? 0, which means the work net is what? 0, which means the work of the guy is equal to the work of friction, right? Which makes sense because look, work net is going to be F net times displacement. What did we say the F net was? F net was what? 0, so work net is 0. That just kind of connects chapter 4 and chapter 5. You guys follow that? Okay. Last thing, the very last part of chapter 5 is force versus displacement graphs. Force versus displacement graphs. So there's two things to know. And I want to take this off here. The two things to know on a force displacement graph. 1, the slope of the line. The slope of the line is equal to the spring constant if it looks like this. You know, this is the type of graph you would get when you stretch a spring. Because why does that make sense? As you grab a spring and start to pull it, what happens to the force of the spring? The farther you stretch the spring, what happens to force? The force goes up. Okay? The slope of this line is equal to the spring constant. So let's just review spring constant. We already talked about this last week, but let's talk about it again. Let's say that this spring right here has a spring constant of 100 newtons per meter. I like 100, it's nice and easy. Just be aware all springs have their own spring constant. So if we take this spring and we stretch it 1 meter, right? And to the right is plus, to the left is minus. That's our sign convention. What force would this spring be exerting back? So it'd be 100 newtons negative, meaning to the left, right? So the equation that we're using here is called Hooke's law. Force of spring equals negative K delta X. What's this negative all about? Negative Kx. The negative simply means the force of the spring will always be opposite the displacement. If you pull a spring to the right, the force will be to the left. If you push a spring to the left, the force will be to the right. Does that make sense? Okay. So what if we pulled this spring 2 meters? If we pulled it 2 meters, what would the force be? 200 newtons. Okay? So check it out. If you're given a graph like this for a spring, you can figure out the spring constant. Because what's the slope going to be? If you calculate the slope, what are you doing? Slope is rise over run. So pick 2 points on this graph, boom, and then pick the other one as 0. That makes it nice. What is the rise for this situation? The rise is the what? The force. What's the run? That's the displacement. Look at, take Hooke's law. What's K equal to? Force over displacement. So the slope is equal to the spring constant. Make sense? Okay, second thing. The area under the graph is equal to the work done. So looking at this graph here, if you calculated the area under that graph, how would you be doing it? Well, it's a triangle, so you have to include 1/2. But basically, what are you doing? After the 1/2, you're going, it's 1/2 base. What's the base measured in? That's displacement. What's the height? The force. This should look familiar to you. Just rearrange it. F, just put it the other way. What's F delta X? That's the work, right? That's the work. Now, why do we have to have the 1/2 here? Why does the 1/2 have to be there for this situation? Well, is this a constant force or not constant? It's not constant. So basically, the 1/2 is giving us the average force, right? By putting the 1/2 in there, it's the average force. So say, for example, the force up here is 200. So look, what does the force start at down here? 0. It ends at 200. So what's the average force? 100. That's why we're doing the 1/2. You're using the average force. You like this. I know you do. And then I promise, final thought, final. I know this is a long lecture. Be aware that you could have problems where, you got force like this, like that, and the graph goes like boom, boom, like that. So look, what's going on here? This would be what? Positive work. This would be what? Negative work. What does negative work mean? Opposite motion. Positive work is with the motion. So what if you wanted the total work done? The total work done is you'd calculate this area, find that work, whichever one's bigger wins. Okay, let's look at a homework problem.